Solving quadratic equations by square roots. So there are actually four methods to solve a quadratic equation, and this is the first of the four. So let's talk about the kinds of solutions you can have with quadratic equations. We can have one real solution, which means you cross the x-axis one time. You can have two real solutions, which means you cross the x-axis two times. Or we can have no real solutions, which means you don't cross this x-axis at all. But just because you have no real solutions doesn't mean you have no solutions at all. This means you have imaginary solutions, which means your solution will involve the square root of a negative number, or in what we change into I. So let's do some examples. So solving quadratics using square roots. This method can only be used when you have one x term that is squared. And so even if there's an x squared and an x, you cannot use the square root method with that example because there are two terms with an x. And so here's the general idea. First, you need to isolate the squared term or terms. Whatever is squared, get it by itself. Then you're going to undo the square by using its inverse, which is the square root. So just like addition and subtraction, square roots and squares are inverses of each other. Step 3 is simplifying the radical if you need. So for example 1, solve 5x squared plus 2 equals 82. So step 1 is we need to isolate this guy that is squared. Notice how I did not box in the 5 with the x squared. So there's two cases you can have. If there are parentheses around 5 and x with the square on the outside, this means that both 5 and x are being squared. But if we just have 5x and then a square with no parentheses, what this really means is 5 times whatever x squared is. So the only thing being squared in this case is just the x. And so these parentheses are not giant symbols, but they do mean a lot in terms of what math is actually going on. So let's go back to example 1. How do we get the x squared part by itself? Well, you're going to solve like normal. We're going to subtract 2 from both sides. And we end up with 5x squared equaling 80. And then I still need this x squared by itself. So we're going to divide out the 5. And we end up with x squared equaling 16. Now that we have the squared part alone, this is where you have to undo the square, just like you would undo division. So to undo a square, we need to take the square root of both sides. So when you take the square root of something that is squared, really what happens is the square root and the square are inverses. They undo each other. They're going to go away. So all that's left is just whatever's left underneath the square root symbol, which in this case is just x. Now, for the square root of 16, I'm going to put that here for now. The square root of 16, though, is a nice number. This is a perfect square. So that means we're going to have an x equals 4 because the square root of 16 is equal to 4. 4 times 4 is 16. However, this is not the only solution. The other solution is also x equals negative 4 because negative 4 times itself is still 16. And so when you take the square root of a number, you will always have a positive and a negative version of that square root. Positive 4, negative 4. Pause the video, try example number 2. So here we have x squared equals 18. And so if we try to take the square root of x squared and 18, the left side, the square and the square root will cancel and we get x equals, but then we're left with the square root of 18. But remember, we also have negative square root of 18 as well. And so what we need to do is 18 is not a perfect square like 16 was. And so we actually need to simplify the square root of 18 down to something smaller if we can. That doesn't mean make it a decimal. So decimal answers are approximations. I want an exact answer, so you're going to have a square root left over. So how we simplify is we break it apart into its factors. So one factor of 18 is 2 times 9. And then I can break down 9 into 3 times 3. And so we look for pairs. So in this case, I see that I have a pair of 3s. So that pair of 3 is going to go outside the square root symbol. And then we leave whatever was without a pair inside. And so our answer for this portion is x equals 3 square roots of 2. But remember, we had this side as well. Now, you don't have to do the same process again because square root of 18 and square root of 18 will always simplify down to 3 square roots of 2. It's not going to change from one problem to the next. So what we can do is we can say, well, this will be x equals negative then square root of 18 is 3 square roots of 2. Well, a negative times a 3 is just negative 3. So you can leave it as negative 3 square roots of 2. That would be your second answer for this problem. So if you do not have a perfect square underneath, then simplify that square root and then see if you need to get x by itself any further. Let's look at example 3. So for example 3, we have something squared other than just x. So in this case, what's being squared is the entire x plus 1. So we need to get x plus 1 squared by itself. So we need to add 3 to both sides. And so we're going to end up with 3 times x plus 1 squared equals 12. Now, we need to get x plus 1 squared by itself, but we can't distribute out the 3 because order of operations says that exponents must come before multiplication. So instead of distributing in, we're actually going to divide the 3 out. So 3 over 3 makes a 1. So we have x plus 1 squared equals 4. Now that we have what is squared alone, we can solve this for x. So to undo a square, we take the square root of both sides. So this square root and this square are inverses, so they will go away. And what's left is x plus 1. Now, the square root of 4 is a perfect square. So the square root of 4 is equal to 2. And the square root of 4 is equal to negative 2. So we still have 2 answers here. Now, the last few examples, we were finished at this point because x was already isolated, x was by itself. But now we have x plus 1. So we still need to solve both of these smaller equations for x. So that means we're going to have to subtract 1 from both sides, which makes 1 as my solution. And then also subtract 1 on this side. Now notice that this is a negative 3. So just because this answer was a 1 doesn't mean this is going to be negative 1. You have to be careful. This is where you do the opposite, not at the end. So for example 4, let's look at this one together as well. So again, this is what is being squared. So I need to divide out 7, divide out 7. So we end up with x plus 2 squared equaling negative 48. Well, to get the square away, to undo the square, we're going to have to take the square root of both sides. So the square root and the square are inverses, so we end up with x plus 2 equaling. So we end up with x plus 2 equaling, well, let's think, square root of negative 48. Well, negative 48 is not something that I can take the square root of at all, because no number times itself will end up with a negative. So normally, back in Algebra 1, you would stop here and you would say that there is no real solution, which there isn't. There is no real solution to this. This is an imaginary solution. But we're going to actually continue and find the imaginary answer. So x plus 2 equals the square root of negative 48. But remember, you can also have x plus 2 equaling negative square root of negative 48. Positive version and a negative version of the same number. Continue solving for x. Well, I need to simplify the square root first. Well, simplifying the square root of negative 48 is very similar to simplifying the square root of 18. So we're going to break this apart into negative 1 times 48. And now I can break apart 48. 6 times 8 makes 48. Let's break apart the 6 into 3 times 2. And let's break apart the 8 into 2 times 4. Then the 4 gets broken down into 2 times 2. So now that everything is broken down and all we have left at the bottom are primes, we need to look for pairs. So there's a pair of 2's here and a pair of 2's here. Just because they're on different branches, it's fine, but they're still pairs of 2's. And so to simplify this, this is going to be 2 times 2, 1 for each of the pairs, then square root of whatever's left without a pair. So that would be negative 1 times 3. Now we can take this a little bit further. We know that the square root of negative 1 is an I. That's what makes this an imaginary solution. So 2 times 2 makes 4. The I comes out of the square root, and then we are left with square roots of 3. So what we have done is we have simplified the square root of negative 48 into 4i square root of 3. So here's what we have so far. We have x plus 2 equals 4i square roots of 3. But we also have x plus 2 equals negative 4i square roots of 3. We simplified the square root of negative 48 on both of these equations at once. We've done both of this at the same time. Now we need to solve this for x because x is still not by itself. And so the way we get x alone is we're going to subtract 2 from both sides. However, we cannot subtract a 4i square root of 3 and negative 2 to make this entire thing 2 because this has an I and this does not. So what that means that these are not like terms. So I'm going to put the negative 2 first, and then I'm going to put plus 4i square root of 3 because this is a positive. The reason why I put the negative 2 in the front is because if you put it at the end, it may look like it should be underneath the square root with the 3, which it's not, which is why we just put the negative 2 up front instead. Now, same thing for the right side. We're going to subtract 2, subtract 2. And again, we cannot actually combine negative 4i square root of 3 and negative 2 to make this entire into a negative 6 because one has an I and one does not. So same idea. Put the negative 2 in the front minus 4i square roots of 3. So this is the imaginary solution for this quadratic equation. So yes, there is no real solution, but there is an imaginary solution here. There's two imaginary solutions. So depending on what the question asks, you may be able to stop at no real solution, or you may have to continue and get the imaginary solution at the end. Let's look at example 5, and then you guys are going to try example 6. So for example 5, we need to isolate the squared part first. So we have to get rid of that 2/5 in the front. So 2/5 times x plus 3 squared equals 6. Well, if I want this piece by itself, I would have to divide by 2/5. But dividing by 2/5 is not the easiest thing to do. So dividing by a fraction is the same as multiplying by its reciprocal, the flipped version. So we're going to multiply both sides by 5/2 because 5/2 times 2/5 is still a 1. And 1 times x plus 3 squared is still just x plus 3 squared. Equals, so 6/1, 6 times 5 makes 30, and 1 times 2 makes 2. But I can simplify 30/2. So x plus 3 squared is actually equal to 15. Now that we have the squared part isolated, we need to undo the square by taking the square root of both sides. So we end up with the square root and the square cancel each other out, and we get x plus 3 equals. Now, square root of 15 is not a perfect square. So I'm going to have the square root of 15, and I'm going to have x plus 3 equaling negative square root of 15. X is not completely alone just yet, though. So let's try first to simplify square root of 15. So if I try to break apart 15, I get 3 times 5. Well, neither of those are pairs, and they're both prime numbers. You can't break down 3 or 5 any further. So there's no way you're going to be able to get a pair out of 15. And so what that means is that the square root of 15 cannot be simplified, and that's fine. Which means we're just going to have to leave it as square root of 15. So I'm going to go ahead and erase this little tree here. So we're going to leave square root of 15 as square root of 15. Since it can't be simplified, we're going to leave it alone. So now to get x by itself, we're going to subtract 3 from both sides of the equation. Now, square root of 15 is an actual number. This is a decimal. It just doesn't end. It doesn't repeat. This is an irrational number, kind of like pi. And so again, we don't want to get the decimal approximation of this because then I'd be estimating and I want an exact answer. So instead of getting a decimal and then subtracting 3, we're just going to simply write negative 3 plus, because there's a positive here, square root of 15. This is a numerical answer. It doesn't look very nice right now, but it is a numerical answer. Take negative 3 and add it to whatever decimal approximation square root of 15 is. And then on the right-hand side, same idea. Subtract 3, and again, we're not going to get the decimal approximation, so we're just going to have negative 3 minus square root of 15. And the minus comes from this negative in front of that square root of 15. Pause the video, try example number 6. And here's your solution for example 6, 3 and negative 3.